Good afternoon, everyone. I hope you are doing all right and ready to learn some physics. So today we're going to be starting a new chapter, waves. And if you recall from physics 1, towards the end of semester, we talked about oscillation, like a motion of pendulum, motion of mass attached to a spring. So those kind of oscillation creates basically waves. Okay. So once the oscillation, causes the disturbance, for example, in this case, let's see if we can see that this ball splashed on the water, it is creating disturbance. And if we were to keep repeating and bumping on the water, what's going to happen? There are going to be this succession of this disturbance, what we call wave, are going to show up and propagate through the medium in this case. And similarly, you can also generate disturbance or wave in a string. And in the games, sometimes before a game starts, sometimes they start, generating these waves. So what's going on there? These people are not moving from one place to another place. But what happens? They just raise their hand. So their hand is just oscillating up and down. But the wave of the hand is kind of moving. So in this case, what happens is, in case of disturbance, when it's moving, it is a pretty good example to understand how the wave propagates. So only the oscillation moves, but the oscillating object or the medium that helps for this disturbance to move is not moving. Medium itself is not moving. Okay. So for example, over here, rope is there, but the disturbance just moving. Okay. So in this case, what is disturbance doing then? Is just transferring the energy. Okay. So for example, here in the water ripple, that's if you are standing near the, on the, let's say, some sort of water body, and even more prominent if you are on the ocean. So what happens? The wave comes and crashes on you and it pushes you. So that means it has energy. So it is carrying that energy. Okay. So now there are mainly we can divide waves into two kinds of waves based on how it propagates through a medium and what the medium is doing. Okay. So when I say medium, medium is like a rope or water, okay? And the wave itself is a disturbance. That means in that particular moment here, what's happening, this string is particle on the string, they are moving up at this moment. So that's why we see this bump. And all these particles are not moving with the same speed. Here they are just they are not, like let's say, move to a same displacement. These in the front, they are just starting to move up, and then it has already reached to the highest point, and these points are already coming down and in the process of becoming straight. So that's what's happening. So speed of a disturbance or wave on a string can be written as this equation. Here T is tension in the string, so that means if the string is tighter, what happens? Wave moves faster. And this is called linear mass density of the string. So the density you learn in physics 1, that is mass divided by volume. Okay. Usually when we say density, we mean mass per unit volume. But if we have a straight thing like this that doesn't have much volume, then it's a good idea to define density in terms of length. Okay, so what is this then? This is mass per unit length rather than the volume. So if you know all length of the string and you know the total mass of the string, you divide mass by length, you get this linear mass density. Just like if you want to find density of water in a bucket, you find the mass of the water in the bucket and you find the volume of the bucket where the water was, okay? Uh, and then you just divide. You do the same thing here. You find the mass of the string and then divide that by the length of the string this time rather than the volume. Okay, so now in case of transverse waves, what happens? Direction of oscillation and the propagation, they are perpendicular, they are 90 degrees to each other. So in the spring or in the rope, that we can generate wave by just attaching a rope in one side and then shaking up from the other side. It is transverse wave, an example of transverse wave. And the water ripples, they are also example of transverse wave because the ripple, they are going up and down but also moving along the surface. Okay, and the longitudinal wave, where the speed and the oscillation happens in the same direction, or the medium of the particles are moving in the same direction. So here these springs are moving back and forth horizontally in this case. Okay, and at the same time the wave is also moving horizontally. So in this case, unlike in the case of transverse wave, what happening? The motion and oscillations are in same direction. So when it is oscillating, what happens is it generates a pocket of compressions and then a pocket of rarefaction. So where this spring coil, for example, are a little separated, that's the rarefaction. And where they are close together, that is compression. And notice they repeat in equal time interval. For example, here versus here. So if we were to measure from center to this center to that center, and that is also going to be equivalent to wavelength of this wave. In case of transverse wave, so for example, if you are looking at water ripple, so distance between two, let's say high on the wave or the crest, that is called one wavelength. We'll talk a little bit more about that. And like in the spring, what happens if on the air or gases, similar pattern happens. There is compression and there is rarefaction region. So this is also an example of longitudinal wave. And when we speak, the air in front of us, or when as the disturbance passes and reaches to the other person's ear and can hear, right? So in that case, what's happening? The air molecules are doing this kind of dance over there. Okay, so these are two kinds of waves. So in both cases, these waves are moving. Okay, so their position with time is changing. So here is a snapshot of a typical wave. In this case, this is not a time. Sometimes we may plot time, sometimes we may plot just the position of the wave. So for example, this position is position, for example, along the string or the water surface, something like that. Okay. So now this is a disturbance, and here it looks like it's a longitudinal wave. But even the transverse wave can be plotted something like this. So this is just the displacement from the some equilibrium point. So for example, if we go back and look, so let's say if we were to say this is equilibrium point, then how far the middle of the rarefaction is, we can say, okay, that is the displacement in one side and displacement in the opposite side. So we can think of this being something like that and that being something like this. So if you were to rotate 90-degree here, and this is how it's going to look. So both kinds of waves can be represented by this kind of a sketch. So where the maximum or minimum occurs, those are some special point where the maximum is occurring. We call that crest. And distance between two subsequent peak or the crest is known as wavelength, and it is denoted by this Greek alphabet lambda. And it is called wavelength. So farther the separation between these two consecutive crests are, we say, okay, longer the wavelength is, and vice versa. And same thing goes with the trough as well, or the valley, right? So this is also one wavelength. If we look at here, there is zero value, and first zero occurs here, and then this zero repeats here. See how it is going in this direction? Similarly, this is also going in that direction. So this is exactly same point as this one. So this is wavelength in this case, not this one. This is not the wavelength. Rather, this whole thing is wavelength. This is just half of wavelength. Okay. And from peak to this zero value, that's going to be quarter wavelength. We can tell, right? So we learned that this kind of sinusoidal oscillation can be represented by using either sine or cosine function, with maximum displacement being the amplitude, and that's what I am showing here, right? So that is the amplitude. So these are amplitudes. So that is from the mean position. Okay. So for example, if we were to go back here, what is amplitude here? So for example, if this is mean position, then this is amplitude. This is amplitude. If I were to do this here, then from the center here, one side amplitude, another side amplitude, or negative amplitude. One side is positive, another side we can say negative. Okay. So this is basically a sinusoidal function, and this is like an angle theta, or could be written as a omega t, because theta is equivalent to omega t, and omega can also be written as a 2 pi over period, right? And these things we learned in physics 1 when we talked about oscillation or rotational motion or circular motion. Okay. So this is called angular frequency, but we can also write this angular frequency in terms of linear frequency. When we do that, this becomes 2 pi f. So that's why in the wave equation you can see sometimes it's written as a f, sometimes it may be written as a omega, sometimes it may be written as a 1 over period for this one there, assuming 2 pi is here. Okay. And this is wavelength, and this positive and negative sign simply tells us whether this is propagating to the right or left. So it's kind of opposite. If it is positive, that means it's moving to the opposite of positive x. And when it is negative, that's when it is moving towards the positive x direction. So it's kind of opposite. So we can see this by plotting this equation using some sort of plotting program, but I'm not doing that here. So in this case, it involves time. This involves position. Okay. So now what is this then? There is no time here. So this is just like, this thing is, let's say wave is propagating and you take a picture. So you froze that on the, so I just noticed there is a message on the chat. So I thought the direction of the wavelength was when it changes from below x axis or above the x axis. So yes, you can measure from different places because it repeats, right? So from top to bottom, sorry, the top to top here, or from here to here, or from here to here, but this is not wavelength, okay? This side is amplitude, so that's what it is. So I was talking about, okay, then how this equation and this picture is related. So it is like when wave is moving, you take a picture, then what do you see? So there is, let's say there are ripples coming in the water. You take picture of ripple. So you froze that in a time. So you took that at a particular time. So you put some value of time here. And then now it is changing with position. At some point there is crest of the ripple and so on. Okay. So this is basically frozen in time or at a fixed time. This equation is going to give us this. Okay. But if we want to plot time, then we are looking at a fixed point. So how things are moving up and down at a particular point on the water or on the string and so on. Okay. So to see both, yes, we need to do animation, but when we are drawing this still diagram, and that's what we are doing. Okay. So that is speed of the wave, amplitude, and wavelength. Now, frequency, I already talked about. It is 1 over period. And what is period? Time for one oscillation. So right now we are plotting position in horizontal axis. So that's why distance between these two are the length. But if I was plotting this as a time, then distance between these two would be period. Okay. So period and wavelength, they are kind of appears depending on what we are plotting here in the horizontal axis. And the speed of this wave is product of uh, frequency and wavelength. You know, speed is distance divided by time. So for a distance of one wavelength, period, or the time is one period. So this lambda over t, or t can also be 1 over t can also be written as f times lambda. So that's how we write this. Okay, so frequency is 1 over period, and then there is this wavelength. So that gives us the speed equation like this. Okay, and there is one more thing related to this plot, phase. So phase is basically a fancy way of saying angle. Okay, so here looks like I use this notation. Sometimes we may use this. Both of them are called phi. This is a bit fancier than this one, I guess. Okay, but both of them are same thing. So just like I was saying, phase is a fancy, or let's say, yeah, fancy way of saying the angle. Okay, so when we say phase, basically we are interested in phase difference. So difference between 2 points. So for example, if I look at here, what happens here? It's starting from here. When it arrives here, this is a quarter cycle. This is over here, it is half cycle. This is 3/4 cycle, and this is full cycle from here to here. Okay. So full cycle is 360-degree, right? So one wavelength is equivalent to 360-degree. So that means quarter wavelength, this one, quarter cycle, is equivalent to quarter of 360. That means 90-degree. Okay. So what's the phase difference between this point here and that point over there? 90-degree. Or in terms of radians, that's going to be pi over 2. Okay, 90 degrees, because 2 pi is 360. So that gives us 90 as pi over 2. And if we go from here to here, so the phase difference between these 2 points is half cycle, and half cycle is equivalent to 180-degree or pi radians, and so on. So that's what the phase means. Okay. Now with that, let's look at what happens when we mix two waves together. Okay. So we follow a rule called principle of superposition. So this is how the wave behave when we mix two waves, or even it's true even for more than two waves, but we'll be just talking about two waves here. Okay. So when we mix two waves, for example, there is amplitude of one wave, and this is amplitude of another wave, denoted by A1 and A2. So when we mix together, we get total amplitude equal to sum of these two. Okay. So over here, there is maximum, there is maximum, and so on, right? So that becomes total amplitude. So when we mix a wave that has amplitude like this, two waves, then the total becomes sum of that. So here is such a diagram here. So this one has amplitude A, and this one also has amplitude A. Okay. So now when we mix these two together, this is how this looks like. Now it is bigger wave with the amplitude double. And why it's exactly double? Because they are in phase. See, wherever this is peak, this is also peak. Wherever it is trough, this is also trough or valley. So when they are overlapping in phase like that, we say in phase. And when that's the case, we say, okay, phase difference is 0-degree, okay, or radian. It's the same for 0, okay. So, and that's what happens. So it looks like there is another question. I thought the period was how long it took something to go from point A to point B. So here in my sketch, I don't see point A and B. This A here means amplitude, okay? So point A to B, so what points, right? So we have to be more specific about point A and B, what point A is, what point B is, okay? So if we just say going to go from point A to point B is a period, that is not correct. That is some time, okay? So for example, let's say going from Denver to Colorado Spring. Denver is a point A, and Colorado Spring is point B, let's say. So is that a period?
I have, so this, I asked this question and I guess I worded it in a weird way. I was just wondering, like, is period how things travel from one place and back? So, like, in this case, let's say the other A is B, just to visualize it better. So A to B and then back to A.
Yeah, round trip is a period, yes, for the oscillation, if that's what you are saying.
That
So
makes sense. Thank you.
right? So for example, if I make it oscillate, I don't know how good you can see. Let me stop sharing here. So from here, if I let it go, it goes and comes back here. So going from here to there and coming back is one period. Or if you start from the center, going from here to there, coming back here and going other point and then coming back is one period. Okay, it has to be one complete oscillation. So time for one complete oscillation is a period. If point A and B are associated with those, then yes, otherwise no, okay? Okay, so that is the principle of superposition. So now let's take a look here, this question. Oh, I haven't started my clicker yet. Okay, go ahead and you have now a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do. So we have all of these except E. So more C. So C is correct answer in this case. So they are in phase. So that means in phase means they're this and that lining up exactly along the same line. So the phase difference is 0 between them, okay? So that's what they are in phase means. So it doubles just like we saw here. So they are in phase. So A here, and this is now 2 times A, okay? So now here is another question. So this time it says point is out of phase. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do here. So mostly A, but there are other as well. So A is correct answer. So out of phase means something like this. So this is, see on this side, this is crest, and there is trough or peak and valley lined up. So if this is positive A, then this is going to be negative A. So when we add positive A and negative A, we get 0. So before we added both positives, so we got 2 times A. Now we got exactly one is positive A, another one is negative A, for example. So in that case, what happens? This basically collapse, and this mixing of waves or superposition of wave is also called interference. So in this case, what happened? Two waves basically, when mixed, they collapsed. Okay, so you get something like this. So this is called destructive interference, and the previous example was constructive interference. And now there can be also partial. So we may not have always peak matching with peak or trough matching, peak matching with the trough, but maybe slightly off. Okay. And by the way, in this case, the phase difference is exactly pi because its peak is here. So its peak is at this half cycle, right? So the difference between these 2 points are pi radian or 180 degree. So it's like saying, okay, this is 90 degree, and this is 180, and this is 270. So that means difference between 270 and 90 is what? That is 180. Okay. In a cycle, if we start from here, 0, 90, 180, 270, then over here 360. So that is one complete oscillation. So in terms of phase or the angle, that's how we can read things in a oscillation. Okay. So now if there is partial overlap, not constructive interference or destructive, exactly, then it can be partially constructive, for example. So in this case, how do we figure out what's the amplitude going to be over here? So if we follow this line, this is exactly A, let's say whatever that is. Over here, what do we see? This is on the negative side, maybe 3/4 of A, but negative, like 3/4, something like that. All the way here would have been negative A, but this line is crossing at this point somewhere around 3/4, for example. I'm just throwing a random number there, okay? So now, if you add these two, then what happens? It becomes 3/4 A, or if I factor this, it becomes 1 over 1 minus 3/4. So that gives A times 1 over 4, or quarter A. So that's why you see at this point it is only about quarter A positive, so that's why it is on this side. So for each point we can do this math and then figure out what's gonna we get, okay? And we can write mathematical equation something like this, which I'm not proving it here. It is also sinusoidal, and it depends on the phase difference between two waves, okay? So anyway, if it's not fully constructive or destructive, then in between is partial interference, okay? So now let's look a little bit in detail about these two waves mixing or interfering, okay? So let's think about two waves, one moving to the right If it is moving to the right, it has negative sign in the equation. When it is moving to the left, it has positive sign in the equation. It is exactly opposite of our intuition, by the way. Okay. So if we were to mix this, what do we get? We get something like this. So we get just one of those. So basically, it follows the principle of superposition, and we get something like that. But since they are moving in opposite direction, what happens is they can form what we call standing wave. So that means this wave is now these things are not moving. These peaks are not moving. Of course, in this case, they are moving, but here these peaks are not moving. Rather, what they are doing is they are oscillating up and down, for example, in this case. Okay. So that's what each of the points are doing the same thing, oscillating up and down, for example. So here I have a video. Let's see if that thing works. That basically shows, I have a video that shows, see how we can generate waves moving into opposite direction. So in this video, what you see is there is a long kind of string kind of thing. It's kind of coiled spring. So it is tied to one end. Another one is being held, okay, so that you can set up oscillation. So when you set up a disturbance, it moves and hits the boundary here where it is attached, and then it comes back. It gets reflected. So now if you keep doing this, then what's going to happen? There's going to be some wave moving, you know, towards this point where it is being attached, and there's going to be reflected wave that's coming in the opposite direction. So these are like example of waves moving into opposite directions. Okay. So now I'm playing this video and let's watch what you figure out. So see, you see the disturbance goes and hits that place and then gets reflected. And notice when it is the boundary, the disturbance basically came in opposite direction. So before we move on, let's see here. So this disturbance right now came from the left side on the screen, but it went from the right side and comes from the left side. You see that? So it reverses the peak when it hits the boundary, fixed boundary, and then comes back. That is another information you want to keep in mind. Now it is oscillating. So there are these two fixed points called nodes, where one is where person is holding the rope, another one is where it is fixed over there. And in between nodes, there has to be antinode. Now you see there is one extra node in between, near the middle of that string. So now you have two antinode. A here means antinode. So that's how you create a standing wave. So in this case, the disturbance is not moving anymore. It's just going left and right in this case. Okay, so that's why it is called a standing wave. And depending on how quickly, what's the frequency of oscillation, it may generate different number of nodes and antinodes. Okay. So by basically doing this, for example, when you are plucking a guitar string, you are setting up standing wave, and depending on your length of that string and your plucking, it's going to set up different frequency, and different higher notes depending on how it is vibrating with how many notes and in antinodes in between the points where it is, like held at one point, another point you pluck, right? So two fixed point, and then there is this string vibrating in the guitar. So let's talk a little bit in detail here. So for example, basic one, remember when we are fixing it here, it has to be node here, just like the person was holding here, and another end was, tied to some place. So in between nodes, there is always this thing called antinode, where it is vibrating maximally, okay? So now let's suppose if this was, like wave, so here we just constraint this one right there, but let's say if there was further this one like this, then this one would be one complete oscillation. So looking at this in between these 2 points, this looks like a half of a complete wavelength. So length of the string between these 2 points is L, and that is equal to the half of the wavelength. So it seems like distance between node and node is equal to half wavelength, and distance, so that is distance between node, and distance between node and antinode is quarter wavelength. So keep this in mind, and this is going to come out handy. No matter what kind of standing wave you are looking at, based on the definition of wavelength, we can tell distance between two consecutive nodes are always half wavelength, but distance between a node and then next antinode, like this, is quarter wavelength. So this is also quarter wavelength. So quarter plus quarter is half, and that's what that is, okay? So now, once I do that, I can write the relationship between wavelength and the length of the string. So this is also called fundamental mode of vibration. We cannot have simpler than this pattern, okay? And sometimes we may denote that by n is equal to 1 mode of vibration. So mode of vibration is n is equal to 1. So what is the wavelength of this wave? So by just looking at this equation and rearranging, we can solve this one wavelength. So this gives us 2 times L. So that's what I am writing here, okay? And this mode, n is equal to 1 mode, or the fundamental mode of vibration, has frequency what we call f1. And if we know the speed of this wave, and speed of the wave simply depends on, see, the property of the string and how much tension is there. So by measuring the tension and the mass per unit length, we can figure out speed. So if you know the speed of the wave, so once you calculate speed and once you figure out what the wavelength is, you can calculate frequency. Okay, so for example, frequency, wavelength, and speed, they are related by this equation. So that means frequency is V over wavelength. So it's going to be V over wavelength. And in this particular mode of vibration, wavelength is equal to 2 times the length of the string between the nodes. Okay, so that is the frequency. So you know speed of the wave, and if you know the length of the string, you can tell with what frequency it's going to vibrate. Okay, so that's how we can calculate that. So anything you like to ask here, folks? If you're planning to write on the chat, choose everyone and then send it rather than sending directly to me. That way everyone can read what the question is. Okay, looks like we are good. So here is a question for you then. So here length of the string is L. How this length is related to wavelength of this wave pattern, just like we had here. We had length was equal to half wavelength, right? Now I'm asking you, how is length related to wavelength of this wave, assuming again the wavelength is, the notation of wavelength is lambda. So I'm giving you some choices. So if you don't find any one of those, then you can choose this one over there. Okay, with that, I'll let you poll, and you have a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see how we got. Here we are getting all of them. There is d little bit more, which is lambda over 2. So what's the difference between what we had here versus now? Okay, so over here, see, there was just one antinode in between two nodes, but there are two antinodes. So it's like the previous was just this. Okay, so previous this thing was, this part wasn't there. Okay, now we have exactly, oh, now I cannot erase. So now we are all the way here. So to figure this out, if you can remember one thing, that's going to be very helpful, okay? One or two things, but I will tell you two different way to do it. But if you remember just one, that's going to be good enough. So from node to node is half wavelength, okay? Or node to antinode is quarter wavelength. So this one you want to keep in your head, and it's easy to see. This is one full wavelength, so this is quarter. So now this whole length is housing the full wavelength. The string contains a full wavelength, as you can see here. Okay, goes and maximum, and then comes back to zero position here and goes to the negative side, and then comes back to zero, means this is one full oscillation. This is one complete wavelength. Okay, so that means in this case this is equal to one wavelength. So if you remember this, this is quarter, and this is quarter means half, 3/4, and 4/4 means full. So if you can remember this, it's easy to figure that out. So now if I want to find this frequency in this case, so this mode of vibration is called n is equal to 2. So this frequency would be f2. And now frequency is speed over wavelength. And in this case, speed is v and wavelength is equal to length of the string. So that is that. Now, if we go back and look at our previous one, just like you, many of you identified this as a D. And by the way, what was the correct answer here? C is the correct answer. Let me choose that first. Okay. So if we go back over here, the frequency 1 was V over 2L. Here is V over L. So that means F2 is exactly double of F1, okay? Because F1 was B over 2L. So if I do 2 and 2 here, then this becomes B over L. So that's what we have. So it is exactly double of F1. Now let's do one more. Hopefully this time you will count better than what you did last time if you missed last time. Okay, so this length. So how many wavelength it is housing? Okay, could be fraction, could be full. So I'm opening the poll. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So now let's see what we got here. There is more for B. Let's see if that is correct. So if I were to just count quarters, there is 1 quarter, 2 quarter, 3 quarter, 4 quarter, 5 quarter, 6 quarter. 6 quarter of the wavelength. So this is also same as 3 times wavelength divided by 2. Okay, 3 half. Another way to look at it, it was full here, and this is half, 1 and half. 1 and half means 3 over 2. Okay, so now, so that means yes, B is correct in this case, so getting better. Now, this is third harmonic, so F3 is now V over wavelength. So based on this, how much is wavelength? L is, this means wavelength is 2L over 3. 3. So now this becomes V, and wavelength is 2L over 3. So the fraction of fraction, 3 goes on the top. So this becomes 3 V over 2L. So V over 2L was F1. Okay, so that means it becomes 3 times F1. So see how the standing wave pattern we are creating, these are also called different harmonics. Okay, we are creating is the integer multiple. 1 times F1, 2 times F1, 3 times F1, and so on. Okay, so it looks like there is one more here. So let's quickly pull on this one as well. So this being L. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got. So there are more for A. So from here to here, one wavelength, and from here to here, another wavelength. So 2 times wavelength makes sense. Another way to look at it, if we were to count quarter, so 1 quarter, 2 quarter, 3 quarter, 4 quarter, 5 quarter, 6 quarter, 7 quarter, 8 quarter. 8, 4 is 2. Okay, so this is 2 times wavelength. This is another way to look at it. So now if I were to find the frequency here, for example, this is fourth mode, I guess, right? So in this case, B over wavelength, and wavelength in this case, see, L is 2 times wavelength means, oh, 2 times wavelength means wavelength is L over 2. So I can replace this by length over 2. So fraction of fraction, 2 goes on the top, it becomes 2b over L. And this is also equal to 4 times b over 2L. So why am I writing like this? Because b over 2L was the F1. Okay, so this one was F1, so that means it is 4 times F1. So you see, you get all the multiples here. None of the harmonics are missing here in this case. However, let's say if we leave one end loose like this, where it is free to oscillate, so that means whenever it is free to oscillate, it can be antinode at that point. Okay, so in most fundamental way, a vibration would be node at the fixed point and antinode at the point where it is free. Okay, so it is fixed only at one point. Okay, another point it is loosely put in place so that whenever the disturbance arrives, remember disturbance, what happens? The point just want to go up and down. So it is free to go up and down. Okay, there is a ring, and because of that, it is free to go up and down. So that's what we mean. So there is antinode and there is node, and distance between a node and consecutive antinode is quarter wavelength. So that's why L is that. And this mode of vibration is fundamental mode of vibration for this kind of situation. So in this case, using this, we can solve for wavelength, which becomes 4 times L. So that means frequency going to be first mode or fundamental mode of vibration in this case is this, and B is B, and wavelength in this case is 4 times L. See, this fundamental mode is half of what we had, the fundamental mode. Remember F1 for both side fixed, it was B over 2L, okay? So this is half of this one here. So this is quarter of B over L, this is half of BL, so that means the quarter is half of half. Okay. So that's what we got. So this is fundamental. Then what do we get next? So that means another next mode of vibration, or first excited mode. And these harmonics are also called excited modes. So first excited mode would be, remember, there has to be antinode always. There has to be node because it's fixed and this is not fixed. So now we had already one mode of vibration where there was, where there was nothing in between. Now what we have is one node and one antinode. We cannot have just one node and the vibration, or just one antinode and vibration. So what we have is, now we have one node and one antinode, okay? So if the length of this one is L, what do you think the L and wavelength, how they are related, right? So that's the possible choices I'm giving you here. So go ahead and figure that out and poll, and you have a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So we are getting mostly B and D. So there is 1/4, 2/4, 3/4. Okay, so that means it's 3/4. L is 3/4 of wavelength. So wavelength is 4L over 3. So that means, what is the second mode, or first excited mode of vibration? So this is B over wavelength. That means B and wavelength is 4L over 3 in terms of length of the string. So this 3 goes on the top, so it becomes 3V over 4L. And remember, we had V over 4L as a F1, so that means this is 3F1. So in this case, 2F1 is missing. So when we have this kind of setup, what happens? One mode of vibration kind of is missing, okay? So we say, okay, this is not as rich as the case when both of the end were fixed, okay? Both of the end were fixed. So it is missing this even harmonics. Second is missing, and if we look at this, we can figure out probably fourth is going to be missing here. Okay, so I'll let you pull again. This is L. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so here this is 1, 2, 3, 4, 5. So that means 5/4. L is 5/4 of wavelength. So wavelength is 4L over 5. So that means frequency, third frequency going to be V over lambda, means V over 4L over 5. So that 5 going to go there. So this is going to be 5 F1. So see, the fourth one is missing. Okay. Oh, looks like it's already 3:06. So it's a good time to take a break. So we'll continue on. Oh, so how did we do here? Let's take a look. So mostly A, but still some of you having problem, but I have quite a few of them. Hopefully by the end, you will catch up. Okay, I'll see you in 5 minutes. Okay, welcome back. And I'm greeting you with another question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. Mostly C, and that must be correct. I think 1, 2, 3, 4, 5, 6, 7 quarter. So 7 quarter is the length. So in this case, the mode of vibration, third, fourth, I think, is now 7 times F1. Right? So all the even harmonics are missing in this case. Only the odd harmonics are there in this case. But when both ends were fixed, both even and odd harmonics were present. So this knowledge allows one to, devise this different kind of musical instruments, and then play different kind of notes. So notes related to frequency, and note is related to pitch. So pitch, notes, that's frequency is a number measurements. What we hear is note or the pitch, right? So higher frequency means higher pitch. So this is, standing wave on the string. Now let's talk about standing waves in pipe, where there are other kind of instruments. So here I have a video where you can see modes of vibration. You may already be aware that a longer organ pipe, this is open on one end and also open on the other end, and this is where the air is introduced. Then there is a knife edge made out of wood that the stream of air goes through this hole against the knife edge, and then there's an instability when the air is incident on a knife edge. This instability will cause a puff of air to come out outside of the pipe, and then a puff of air to go inside the pipe, alternating outside and inside.
And there's a particular frequency that's associated with this instability. And if that frequency matches the length of the pipe, then you'll get a resonance in the pipe. Like that. If you move to a shorter pipe, it's built the same way. The length is shorter. You get a higher sound.
Higher pitch.
Shorter. You can, if you blow hard enough in here, force different modes to sound in the pipe. What we were hearing just then is the fundamental mode, the lowest possible frequency that this pipe will produce. But any pipe actually produces a sequence of frequencies that follow at least approximately the harmonic series. So this is the fundamental, the lowest possible frequency. If I blow a little harder, I get a mode that's, for those of you that have musical background, will recognize as approximately an octave above it. Do the same thing on this one. So we get a lower mode, a higher mode, and then there's actually an infinite sequence of these modes that goes up to infinity, and that gives the organ pipe its character, its characteristic sound. Okay, this is a demonstration.
Okay, so that was the pipe that was open on both ends. Here is this animation of pipe which is closed at one end. There is little piston. If you notice, this is open here and there is piston. So that means it's closing that end. And this piston can be moved. So that means length of the pipe can be changed. And here it shows the frequency of this tuning fork that is providing a fixed frequency wave. Okay, and this is plot of wave. So, and this is plot of intensity. And by the way, intensity is directly proportional to the square of the amplitude. So for example, if it is going something like that, that means here that is amplitude. So intensity gonna be higher there as well. But here it's a zero amplitude, means intensity gonna come back to zero. Here again, higher, negative side. Remember when we square it, it becomes positive. So that's how it's gonna oscillate something like that. So it's gonna show you at different frequencies, okay? And also it's gonna change the length and how the sound gonna, be different, how the pitch gonna change, okay? How the pitch changes with the length of the pipe for a frequency, and when we double that frequency and again change the length, how it's gonna change. So those kind of things are, demonstrated here. So, and let me make volume a little smaller because at higher frequency, I may, it may give you a little uncomfort. I do not know. Let's see. Yeah. See here what happened. You are getting maximum intensity. Amplitude is large, okay, at that point. So that means at this length, this frequency resonates. That's what it means, right? So different length resonates with different frequency. And then there are going to be different modes. So this is the fundamental mode where there is node and there is antinode where it is oscillating with maximum value. Okay, so that's what we see. So let's keep playing it. Maybe I'll make the sound even smaller. So now it decreases because it's not resonating anymore because that wavelength does not matches with the length of the pipe. Once it matches again, it's going to start oscillating harder, and that's the resonance again. So notice right now it's 512 hertz. Frequency hasn't changed. Only the intensity changes, loudness changes. Now frequency doubles, goes to 1024. Now you see it already resonated once. Now it resonates at different length than what it was before. Pitch is same because frequency is same, but loudness is changing because of the resonance here. The amplitude is different, okay? Okay, so that's that. So how do we analyze this kind of situation? So in this case, one side is closed, so there has to be node, okay? And this is open, so maximum, it allows for maximum vibration. So this is going to be antinode, okay? So distance between a node and consecutive antinode is quarter of wavelength. So that's what we have here. So 1/4, right? So this is fundamental mode, and the frequency is V over that wavelength, okay? So in this case, the wavelength is 4 times L. Ooh, that is same as when we had a string attached to fixed at one end and was allowed to oscillate back and forth at another end. See, this came out exactly like that, this mode. So now how about the second mode, or first excited mode, or first harmonics? I think that's called second harmonics. So I'm opening the pool. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. So mostly B. I'm guessing that is correct. So in this case, this is quarter. So 1/4. This is 2/4. This is 3/4, right? So 3/4 is this one here. So B is correct answer. Okay. See how previous the L over 4 was just this much here, only this quarter there, right? So let's go back and look. See, only quarter was there. So see the difference and make sure you learn that, right?
I'm confused. Why are they not canceling out? I thought they would cancel.
See, these are not two waves. They are basically reinforcing each other. So there is constructive interference happening here, and there is destructive interference happening here. So that's why it's called a standing wave. Okay. So in this case, they don't cancel. So although you may see it's drawn like this, two of them, right? One node, another one looks like inverted, right? So that's how it may look like. But actually there is only one, okay? Only one that is vibrating up and down, okay? It is drawn two just for convenience, okay? I think that's what So I think in this video we watched, let's see, do I still have that video somewhere? The very first video we watched today, that has one string, and that's how they oscillate. Okay. Let's see if I can find that video here. See how there is only one string, and just in this case it's reflected, right? So it's not at standing mode yet. So this is the fundamental mode that has node, node, and antinode, and it is for the string. It's we cannot see in the air, but when it goes to n equal to 2, later you can see it's the one string, but it seems like it is everywhere. Okay, and that's what we are drawing. Okay, this is just one thing, it's not two things there, although in the drawing it looks like two. So I see the confusion where it's coming from. See, it looks like it's everywhere. Okay, especially when it is in higher mode. If you look at it here, it looks like, there's a closed envelopes. Okay, although it is just one string. So that's why it is drawn like that. And I'm also noticing there is a question, how does it reach a maximum amplitude exactly? So maximum when these two waves, see the waves, they are moving one way and the other. And then what happens? At a point when they superpose by lining up with their, let's say, crest and crest together, that's when the maximum happens, right? Or we say when they interact, mix, or interfere constructively. So now let me get rid of this video. So now here is another question related to that. And by the way, I did not do the calculation of frequency here. Let's do the calculation of frequency. So again, formula for the frequency. So this is second mode, and is equal to 2. Okay. F2 is V over wavelength. Frequency is always equal to speed over wavelength because B is F times lambda. Okay. So we are just rearranging this. When this is 2, we can say, okay, this wavelength is also 2 because in each cases wavelength, they are changing. As we saw, the wavelength are going to be different. So in this case, wavelength is 4L over 3. When I rearrange this equation for wavelength, that's what I get, right? So before, what was the wavelength? Wavelength was 4 times L, right? Over here now, it is 4L over 3. So shorter wavelength now we have, okay? So we can have shorter wavelength, means we can have higher frequency, because frequency and wavelength, they are inversely related. Or other way to look at it is this, frequency and wavelength, they are inversely related. So now using this second mode over here, we get V over 4L over 3, which is 3V over 4L. And we know V over 4L was F1, so that means this is 3 times F1. So it is similar to what we had for this string tied to just one end, right? So even harmonics were missing there, and same thing is happening here as well, okay? So now coming back to this one here, so let's pull on this one. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. So mostly A, and let's see, 1, 2, 3, 4, 5. So yes, 5/4 of a wavelength. 5/4 of a wavelength. A is correct answer in this case. Okay. So that is the equal to the length, means wavelength gonna be 4L over 5. So the frequency this for this mode gonna be V over lambda 3, and these are third mode. So that means V over 4L, and there is 5 in the bottom, so fraction of fraction goes to the top. So it becomes 5 F1. So you see there is no 4, there is no 2, and so on. So only odd harmonics in this kind of pipe. So usually we don't see this kind of pipe when they make pipe. Usually the pipes that they are usually open on both end, okay? And these organ pipes, they have holes. So by plugging in here a hole, you are making the length longer. And when you leave your finger, then now it becomes open at that point. So the effective length of the pipe or this instrument becomes shorter. So you are changing the length. By changing length, you are changing frequency. Okay. And similarly, you can also go to the higher mode by blowing little harder, just like we saw on that video. Okay. So now we have both ends open. So that means this is antinode and this is antinode. Open end means antinode. So when there is, a standing wave. So in between antinode, there has to be at least one node. So that's why this is fundamental mode. Okay. So in this case, this is 1/4, right? And this is 2/4, for example, let's say. So that means this is 2/4. So that's why length is half wavelength. 2/4 is half, right? And this is fundamental mode, n is equal to 1. So wavelength is equal to 2 times length. Okay, so there is only half length is there in this length, means full wavelength. To fit the full wavelength, we need to double this length for this mode. So anyway, so that's that. So now if I were to calculate frequency, again, frequency of this mode is the speed and the wavelength in this mode. So V and wavelength in this mode is equal to 2 times length of the pipe, and that's what we call fundamental. So V over 2L, which is similar to what when we had when both ends of a string were fixed. Okay. Now your turn. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Oh, looks like this was tough. So, oh, 1, 2, 3, 4, a quarter. 4 a quarter of a wavelength. So that means this is a complete wave. See the top crest to crest when you follow just one line here. So this is one full wavelength, or L is equal to one wavelength. So that means, or 4 by 4. So we had, 4, so it becomes easier. And let's say this is second mode, right? Okay, so now what happens here? To find frequency in this mode, we use this over lambda 2, and V is there, and lambda 2 is L. So this is 4 times F1. Remember, F1 was V over 4L. Was it 4L or 2L? What happened here? V over 2L was, okay. So this is this is fundamental. V over 2L, not 4L, but 2L. So that means, let's see, what did I do here? 4 quarter means 1 whole wavelength. So F2 is V over lambda 2. So V over L. So we had 2L, right? F1 was V over 2L. Now this is V over L. So this is half of V over L. This is full V over L, right? So that means it is double of this one. So F2 is double of that. So that's why it is 2 times F1. So double. So we are recovering the even harmonics, just like we had for the case of this. So there is a question on the chat. I thought the L was half of the wavelength instead of quarter for n is equal to 1. Yeah, this is that is correct. But if I'm counting this, I'm counting the quarters, okay? See, this is quarter wavelength between node and antinode, quarter wavelength. So I'm counting 1 quarter, 2 quarter. So that's how I'm counting, okay? So this is 2 quarter. So 2 quarter means half. So that's how we got half here, okay? So that means wavelength is 2 times L. So that's how we got that, okay? Now for the frequency, it is speed over wavelength, so B over 2L. So that's how we got this. So now going back here, we are counting the quarters, okay? This is not half. 1 is not half, it is quarter. 1/4, 2/4, 3/4, 4/4. So that's why the L is here. 4/4 of a wavelength means equal to, sorry, 4/4 of wavelength. So one wavelength is exactly equal to the length of this pipe in this case. So I think that was the confusion, at least I thought. But if you ask something else, okay, great, good to know. Okay. So now let's do another one here. And I'm opening the poll. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So now let's see what we got here. So mostly B in this case. Hopefully that is correct. So this is one. Oh, my bad. So we were in this slide here. So this is 1, 2, 3, 4, 5, 6/4. So 6/4 of wavelength is equal to length of this pipe. One length houses 6/4. So 6/4 is 3/2. That's that. Yes, so B is correct answer. And by the way, did I choose the answer last time? Looks like I did not. And what was the correct answer last time? I forgot. So in this case, 1, 2, 3, 4, 4/4. 1, 2, 3, 4. Yes, 4/4 of wavelength means one full wavelength. So C was the correct answer in this case. Okay, so this has B answer over there. Okay, so now if I want to write the frequency, then is this the third mode? I kind of forgot. B over lambda 3, and that's the lambda 3. B over L in this case. And we had, for fundamental, what we had for the fundamental, looks like we had 2L. So is this second or third? So this is fundamental. This is first. Oh, we already did that, did we not? Yeah, I was looking at, okay. So this is fundamental. So L was 2L, means V over 2L was the fundamental frequency for this, right? Oh, which way I'm going here? Yeah, this is where I am. So F, which mode was that? Looks like this is 1, 2, third mode here. 3 is L V over lambda 3 V over L. This is not L, right? Oh, my bad. This is lambda is 2L over 3. Yeah, that's why I was getting something different, 2L over 3. So this becomes 3V over 2L, means it is 3 times F1. So this open pipe has all the harmonics, okay? So here I chose that, I chose that. Did I not choose here? Looks like I chose. Did I choose that right, or did I make mistake? I guess that was before I chose. Okay, so that's that. So we learn how to calculate the equation for the frequency, right? But how about problem? Looks like I did not bring a single problem here. So you may be asked, okay, what is the frequency? So if it says open pipe, that means it's open at both ends, okay? If it says closed pipe, that means it's closed at one end and open at another end. Sometimes the problem may not be very specific. So that's how you want to keep in mind, okay? So open pipe means open on both, okay? So that means pipe, we need length, right? If length of the pipe is, let's say, how long? Half meter? 0.5 meters, right? So we, if this kind of question is asked, then one thing you can do is, if you remember, then the, open pipe fundamental mode is V over 2L. So that means third going to be 3 times F1, means it's going to be 3V over 2L. So here you plug in L. How about speed of sound in air, right? So here I did not say it. I did not write in the problem, but speed of sound in air changes with temperature. So let's say at room temperature is consider approximately equal to 340 meter per second, okay? So now you can plug in those numbers there. So F3 is 3 times 340 divided by 2 times half. So 2 times half is 1. So this is 680 hertz. Okay. So that's how we can calculate that. So if you don't remember, then so you have to do something. You have to remember how to draw these modes. Like first mode gonna be this, second mode gonna be this, and third mode gonna be all the way here. So there is question, how do we know it's F3? So it says the third mode somewhere, did I not? Okay, third harmonic, okay? So that means it's talking about frequency of third mode, first being fundamental, second is first excited, oh, it could be fourth. How does it count, right? So I guess that's what you are confusing. Fundamental and first harmonic, second harmonic, third harmonic. So if we do that, then it's going to be 4 times F1. So at this moment, I kind of forgot how do they exactly count, okay? So I encourage you to take a look what third harmonic means. It is F3 or F4, okay? So yes, we have to know what harmonic we're talking about. So I'll let you, find that out. And I will also take a look. Maybe ask me next time. Okay. For now, I'll be leaving it here because seems like